Hi, good afternoon. I am Anand Sengupta and continuing the Gravitational Wave at Home series with LIGO India. I'm here with the presentation on detecting and decoding higher multiple gravitational waves from merging black holes. And before I tell you what all this is about, I'd like to congratulate the LIGO India team for such a wonderful idea, where we can actually engage students and astronomy enthusiasts all over India and the world uh, in a time like this. So, astronomy has always fascinated human beings, and this is an area where you really have the freedom to ask the big questions. Some of these big questions are really big. For instance, how big is the universe and how old is it? And in 2020, we are in an era of precise observations where science has met its match in engineering. And we do have gravitational waves as a very real probe of the very, very deep universe. Of course, there are other philosophical questions. And in our quest for those philosophical questions, astronomy also has an effect on the evolution of our society and our culture. So, very briefly, the earliest astronomy was using visible light, and it was the only form of astronomy until 1930s. And if you see this, if you look at this band over here, this is the band of the spectrum of visible light. In fact, the visible light is a very small part of this band. So this is a spectrum of electromagnetic radiation. And when humans looked at the sky in this band, the picture that emerged was of a very serene view of the stars and the planets and the galaxies and so on. And we have the deepest view of the universe using visible light. And it turns out that staring at this night sky is not such a bad idea. It leads to wonderful philosophical questions, including the Olbers paradox. I'm sure many of you know about that. But later on, engineering marvels like radio telescopes developed, and we were able to observe the sky in different bands of electromagnetic radiation. Here is a picture of an array of radio antennas, and inset here is the picture of the Arecibo radio telescope dish. And I put this particularly because we are going to meet this particular telescope, and one of the interesting results that came out of this very soon. And when you look at the universe with radio telescopes, you find that it is not so serene after all. You find that there are violent events in the universe which you could only see using radio telescopes. So certain surprises await us whenever we have changed the way in which we look at the universe. If you go to the extremely long wavelength of microwaves and radio waves, and if you look at the universe, you end up with a picture like this. So this is the picture of the universe seen in the cosmic microwave background radiation, and this looks nothing like what we are used to seeing in either visible light or in radio. And as you know, India's first multi-wavelength space observatory is able to look at objects in the sky simultaneously in many, many wavelengths. And this is of fundamental importance, especially when you're looking at events that are short-lived. So the question we ask is that whenever we have observed the universe in new wavelengths of light, it has led to massive revolutions in astronomy. So it is expected in some way that when we observe the universe in an entirely new way, in an entirely new spectrum, we'll make new discoveries. We'll see things that we have never seen before. And in order to go ahead, and of course, I'm referring to the way of using gravitational wave signals as a probe of the very distant cosmos. And before I make any further progress, I'd like to say a few words about uh, what these are and how they are generated. So we start our journey with Newtonian gravity. And you know that in Newton's gravity, when you have two masses, they attract each other with equal and opposite forces, which is proportional to the product of their masses and inversely proportional to the distance between them. So Newton's gravity describes the gravitational interactions of two bodies, and the potential, gravitational potential, you might have learned that it obeys the Poisson equation. Now, this Poisson equation is very strange in that if there is a change in the matter density, there is an instantaneous change in the gravitational potential everywhere in the universe. And as you know, that since information cannot move faster than the speed of light, this prescription is not consistent with special relativity. So long as you have slow velocities, it works reasonably well, it works fantastically well, but there are no gravitational waves in Newtonian gravity. So we go to a different way of looking at gravity, which is basically Einstein's way of looking at gravity, where it's a geometric theory where one says that there is a curvature in space-time created by mass, and this curvature dictates how mass moves. And there are no forces, therefore freely falling masses move in straight lines. So when there is a dynamics of this mass, when this mass is accelerated, there is a change in curvature of space-time that propagates out in the form of a wave, and this is what we call as gravitational wave. But of course, at low speeds or for very small masses, both the theories of gravity basically give the same answer. And if you're thinking general relativity is a very abstract idea, you only have to look at your mobile phones. Whenever you use GPS navigation, basically the network of GPS satellites actually use general relativity to correct for the time delays. So it is closer than you think. And of course, general relativity has passed many observational tests, including the perihelion advance of Mercury. So here is the sun, and here is the planet Mercury going around the sun. But when observers look at Mercury, they find that the perihelion, which is the point at which Mercury is closest to the sun, actually is not at the same point. It starts advancing. So its orbits look like a floret. And this observation, when you account for everything else, there is a residual of a tiny amount, which is about 43 arc seconds in a century. And this can be accounted for by general relativity. There are other tests of gravity, which include the deflection of light from distant galaxies. So, and because of gravity, light bends. And here is a picture of a luminous red galaxy, which has gravitationally distorted the light from a much more distant blue galaxy. So you see the blue galaxy in the form of this arc. And that is proof that gravity causes light to deflect. It turns out that Einstein's gravity also predicts black holes, and black holes are, as you know, solutions to Einstein's equations. And these were, until very recently, they were mathematical objects in the theory. But now we have seen one. For instance, here is the supermassive black hole in M87 galaxy, and was seen 2 years ago by the Event Horizon Telescope. Here is a result of a 16-year-long study using several of European Space Observatory's flagship telescopes. So astronomers have produced the most detailed view ever of the surroundings of a big supermassive black hole lurking at our galaxy's very heart. And the research has mapped the orbits of almost 30 stars. So what you see here are the orbits of those stars. And when you try to figure out what kind of an unseen mass is gravitationally causing those stars to go in that particular way, you end up with a mass that is millions of solar mass. And therefore, we know that there is a galaxy at the supermassive galaxy at the heart of our galaxy. Supermassive black hole at the heart of our galaxy. Now, general relativity also predicts black holes to inspiral and merge to generate gravitational waves. And this is something, so this is the arrow of time. So if there are two black holes that are gravitationally bound, general relativity predicts that they will undergo an evolution by which they emit gravitational waves and come closer and closer until they merge and form a single black hole. And this is exactly what we saw on 14 September 2015, when the LIGO Scientific Collaboration announced the detection of gravitational waves from two black holes orbiting each other seen in the two LIGO detectors. So what you see here is the data from the Hanford and the Livingston detectors. And this is the second panel that you see here is basically the reconstructed signal that was seen in these detectors. And the last panel that you see here is what is called a spectrogram of the signal. Now, I mention this particularly because in our discussion later on the higher multipoles of gravitational wave signals, I'll come back to spectrogram, and I'll draw an analogy of the spectrogram to something more common that you have seen in everyday life. So please keep this in mind. So that's why there is a placeholder for, for the spectrogram. And the detected signal, of course, lies within the human audio band. So they can be represented as audio signals. Of course, it's an analogy. Gravitational waves are not audio signals, but they can be converted into audio signals. And when you do that, this is what they sound like. So again, so what is happening is this is the spectrogram of the data. And I have not told you what a spectrogram is. But what we are doing is we are scanning through the spectrogram and converting the signal into audio, and that's what you're hearing. So in order to detect gravitational waves, what you need is a very accurate ruler which can measure distances to very, very high accuracy. And several attempts have been made since the 1980s, and the first detection was only made in 2015. And these are basically the LIGO interferometers, which are broadband detectors, which mean that they are sensitive to gravitational waves over a wide range of frequencies, all the way from about 10 hertz to about a few kilohertz. And here is a picture of the LIGO laboratory at Livingston in Louisiana, USA. And these are the two 4-kilometer arms. I'm sure these pictures have been shown by many other speakers on this forum, so I'll not spend too much time talking about them. It turns out that if you have gravitational wave detectors are such that if you have more than one and form a network of such detectors, you can extract the best science out of it. And here is a picture which shows that. So for instance, if you have a network of 3 detectors, Hanford, Livingston, and the Virgo detector in Europe, then you can point to sources in the sky, different parts of the sky, and these ellipses that you see are the errors that you make in your pointing. But if you include an extra detector in India, the same errors shrink in size, and you can locate these sources much more precisely. This is just one example, but there are several where you can argue that for the best science, you need a network of gravitational wave detectors which have very long baselines. From the gravitational wave candidates that we have detected in the first and the second observation run, we have already discovered a new population of black holes with masses that are larger than what have been seen with X-ray satellites. So, for instance, these purple circles are the black holes seen in X-rays, whereas these blue circles point to much more massive black holes that were seen in the LIGO-Virgo network. So maybe we are looking at a completely different population of black holes using the new tool that is at our disposal. Now, when you have binary black hole mergers, so what you do is you take 2 black holes and place them in a binary orbit of each other. Now, as the system evolves, it will emit gravitational radiation in accordance with general relativity. And what will happen is this orbital separation and period, they will keep decreasing with time until eventually the 2 black holes merge. The question is, have you seen something like that? And the answer is yes. So this example is not a binary black hole, but a binary pulsar system, a binary neutron star system known as PSR 1913 plus 16 system. So a pulsar, as you know, is a neutron star that is spinning very rapidly, and as it does, there is a beamed emission of radio waves that are, and if you are in the path of that beam, then you see it once in its period. So this particular system consists of one pulsar, which you are able to see, and its companion, which is unseen because maybe its beam is not pointed towards us. And basically what happens is that if we observe the rate of decrease of its semi-major axis up to 3.5 meters per year, and the orbital decay is 76.5 microseconds per year. So that means it is spinning up so the period is coming down. So that means this 2 pulsars are spinning more and more rapidly. And here is a picture since 1975 all the way up to 2005, where we plotted the epoch at which they came closest to each other. So if they're spinning faster and faster, this epoch will come more and more close to each other. So this is the prediction from general relativity, and these dots that you see, these are basically the observational points. It turns out for this particular system, the advance of the periastron is almost 4 degrees per year, which is much more than what you've seen in Mercury. And because of this discovery, it was awarded with the Nobel Prize to Hulse and Taylor. So now let's look at what gravitational waves look like. And for this, I have a little video for you. So where basically I have 2 black holes in orbit around each other. And I'm just going to pause this video to tell you what you're expecting to see. So basically, we'll follow this evolution of this black holes when they are reasonably far apart. And this trace that you will see is basically the gravitational wave emission trace. And we'll follow it for a few cycles and then cut all the way towards the end when they are kind of merging into each other. So we'll start this once again, and just keep an eye on this trace. And please don't be puzzled if it cuts all the way to the end, because that's how this video has been made. So these are the initial cycles. And this time that you see is the time to merger. And now we have cut all the way over here. And you see that the smaller black hole is about to crash into the bigger one, and it has been frozen for a minute. It forms the final black hole, and it rings down until to get rid of all the gravitational. There's a lot of gravitational wave emission when it rings down. So if you look at the morphology of the shape of the gravitational wave signal, this is what it looks like. So this is time going forward. And for a very long time, you see it looks like almost like a sinusoidal signal, and it is, in fact. And in the beginning, the sinusoidal signal slowly increases in frequency. You see that these troughs and crests occur more quickly as you move ahead in time, until there is a merger, after which the final black hole rings down in the form of a damped sinusoid, exponentially damped sinusoid. So I want you to remember this picture, because we are going to use this to try and understand where the higher multipoles of the signal come from, and what are we talking about when we talk about multipoles of the signal. So if I represent this binary black hole with these two billiard balls marked 8, and suppose they are of equal size or equal masses, and they are going around each other. So in one orbit, what happens is that this ball on the left comes all the way to the right, and this guy in the same time takes the other position. And that's exactly identical to how it started off. So in one orbit, it's going to happen twice. So this symmetry just tells you that the dominant gravitational wave frequency that is emitted is going to be at twice the orbital frequency. Orbital frequency means the rate at which these guys are spinning around. So in one orbit, twice. So the second harmonic is the dominant harmonic, and this is the only harmonic when you have equal masses. So if the two masses are equal, then this is the dominant harmonic. Of course, it can occur at other higher harmonics, but let's not bother about that for the moment. But if you look at the full waveform, it contains other harmonics of the orbital frequency. And let us look at how that might come about. So, for instance, if I take a binary black hole system with unequal masses, so now we are not going to get that symmetry. So in one half orbit, it's not going to be exactly the same configuration as it started. So in the case of unequal masses, it turns out that odd harmonics of the signal are also present. And the most prominent one is the third harmonic. And it turns out that there is a great difference. The more asymmetric these two masses of these black holes are, it turns out that the amount of energy that is there in the higher harmonics also increases. So for instance, here is a little plot which shows you a binary black hole system with one of the masses is 2 solar mass and the other is 10. And you see that the ratio of these two is 5. Depending on how you look at the system, you see that there is a difference between the full waveform, which is the black waveform, which includes all the harmonics, and just the dominant quadrupole or quadrupole harmonic. And this green trace that you see is the difference between the two. But if I now increase the mass ratio to another system where the ratio is 15, so the asymmetry of the two masses is much more, then you see that if you look at in the right direction, it turns out that there is a significant amount of power or energy in the higher harmonics. Now, here is a plot which tells you what is the fractional amount of energy that is there in the third harmonic as compared to the dominant harmonic in this plane where the vertical axis is the total mass and the horizontal axis is the some measure of how asymmetric they are. So if you go from right to left, they become more and more symmetric. And by the color code, you can see that this zone, which corresponds to asymmetric high masses, that is the zone where the asymmetry causes more and more power in the higher harmonics as compared to the dominant harmonics. So if you have an astrophysical system which has high mass and very asymmetric masses, then you would expect to see more contribution to the higher harmonics. Let me bring a musical analogy in order to explain what harmonics really are. So for instance, here is a guitar and you would want to strike a string to play the A note, which is suppose at 110 hertz. Of course, as you know, the guitar is bound at these two ends. And so if you can play the guitar so that the string basically makes a perfect arch between this end and the other end, then of course only the fundamental frequency is excited, and that depends on the length of that string. But that's not how we normally play guitar. How do we play the guitar? We just pluck it, and when we pluck it, we basically lift up a string up to a point and then we leave it. And when we do that, basically all the parts of the string, they try to come back to their equilibrium positions. And in the process, not only is the fundamental frequency excited, but many other frequencies are also excited, as you can see. So for instance, not only is the fundamental frequency, which is the 110 hertz A notes excited, but you also have second harmonic, third harmonics, and so on. So basically, a plucked guitar string plays all these overtones at the same time. And it also turns out that higher harmonics don't change the pitch, but only the quality of the sound, which goes by the name of timbre. So let us see a little video where we will start with a single note and then add higher harmonics and see how that changes the quality of the sound.
If we listen to just the fundamental frequency with no overtones, it's actually just a pure sine wave, and it sounds very boring and very simple.
So that's the sound made by a single note, which is playing at whatever frequency has been set. So you see that signal is basically a sinusoidal signal at a single frequency. And now what this guy is going to do is that he's going to add higher harmonics to the signal, and you will see how it changes. It doesn't change the pitch, but it changes the quality of the sound.
Changing the shape of the sound wave while keeping the same frequency will change how the note sounds, that is, the timbre of the note, but will not change the pitch of the note.
So what he's doing is he's using these keys to add more and more harmonics to the basic note that you saw, and very soon he's going to convert that into sound.
Now, this can be done digitally, but it's also done naturally by instruments. If we add some harmonics, then we can begin to somewhat recreate a true instrument's sound. For example, the sound of a violin.
is a true perfectionist. So you see, it is the same sound, but the quality of that sound has changed. It's the same pitch, but the quality has changed. In other words, the timbre has changed.
Now, this is also
So here is, just to summarize, here is the dominant note, so to speak. And when you add higher harmonics, the signal becomes much more richer and more complex. And that's exactly what happens with gravitational wave signals too. So when you have higher harmonics on top of the dominant note, the signal that you receive from astrophysical objects, merging black holes, becomes richer and much more complex. So here is a picture of uh, one case, the top one being where equal masses, that means, and no higher harmonics were added. And you see that this is the dominant harmonic. And in the second case, we have kept the masses to be the same, the total mass to be the same, the sum of the two masses to be the same. But now we have made the mass ratio highly asymmetric. So one mass is 6 times heavier than the other. And now the higher harmonics are much more prominent. And if you watch very carefully, if you compare these two, you'll see that there is a little bit of wiggle between this and here. So there's a little bit of more wiggle in the gravitational waveform in the lower path. Now the question is, how do you separate out these harmonics if they're present in the signal? And the answer to that lies in a theory of Fourier transforms given by Joseph Fourier, who was a French mathematician. And the idea behind that is, suppose you have these square waves, and this square wave, I'm going to play that again. It can be decomposed into sine waves of different amplitudes, as you see. So if you add up all these sine waves of different amplitudes, the claim is that you end up with this square wave. And this is just an animation to show that indeed that is true. And you look at the amplitude of the different components, and that is what is known as the spectrum of the signal. So this is just like a prism. Just like a prism can separate the colors of white light, when you do a Fourier spectrogram, you can distinguish harmonics that are present in any signal. So here, just to give a better idea, here is a sawtooth wave. So this is a signal which looks like this. And I'm going to show you that this can be recreated using addition of many sine waves of different frequencies. So here is first one. So it starts with a single. So every circle is a sine wave whose radius equals its amplitude. So this is the first one. And very soon we are going to add one more at twice the frequency. And you see immediately the sum total is started to change. And now we add a third one, and so on. So following the same sequence, after we have added many more sinusoidal waves, this is what we end up. So basically, if I add up all these sine waves, I end up with a spectrum which looks like this. So this signal, this is the spectrum of this sawtooth wave. So what is this telling me? It is telling me that this sawtooth wave is a sum, is a combination of the following pure sinusoids in this signal. You can use the spectrum to distinguish the dominant and higher harmonics in instrumental sound. So here is a video to show you that. So the video starts with a pure sine wave at the G note, which is roughly the 400 hertz note. And then you will play different musical instruments and calculate the spectrum of their musical sound, and you'll see how the higher harmonics present in those instruments clearly are seen when you take a spectrum.
G. In this case, 391.995 hertz.
So that's the pure signal. So this is our reference because we know where to look for the dominant note. And now first we'll play the banjo.
Plotted here in the frequency domain. First, comparison with the banjo G. Here we can see the first, second, third, and fourth harmonics, also known as overtones.
So you see that these are exactly at, so this one is at 400, the next one is at 800, the third one is close to 1200, it's not really exactly at 1200, and so on.
In between, we see the subharmonics. Next, the guitar G, where we see the first, second, third, and fourth harmonics with subharmonics.
And you see the
and finally, the synth G, with first, second, third, and fourth harmonics.
So I hope this clears the idea of what we mean by the subdominant harmonics present in gravitational wave signal also. So it's basically we are looking for a dominant component, frequency component of the signal, and an additional very faint component which has to be isolated.
G.
So when we calculate the spectrum of the gravitational wave signal, this is what it looks like. So what are we plotting here? We are plotting time along the x-axis. So as you know, the frequency of gravitational wave increases with time. So if I isolate a little bit of the signal here at this point and take its spectrum, all the frequency is concentrated at about 40 hertz. Whereas if I move ahead in time and come closer to the merger, you see that now the frequency component of this gravitational wave is it is emitting at a higher frequency. And if you go all the way near the merger, you see that the frequency rises very, very sharply. Now, can I use this idea to separate the components of different frequencies that are there in gravitational waves, which may not be very apparent by just looking at the time series? So, for instance, here, if you look at these three plots, you'll see that it is the same system with different mass ratio. And as we have seen earlier, as the masses become more asymmetric, the combination or the contribution from higher harmonics become more and more prominent. So for instance, when the two masses are exactly equal, there is hardly any contribution from, so this is only the dominant mode. But now as soon as I make them one mass twice as much as the other, you see that there is a faint trace over here, which is basically the next higher order mode. And when you make it even more asymmetric, you see that the spectrogram is able to isolate all the other modes that are now beginning to come into the picture. So if you sum up the energy along these tracks, you'll see that as we increase the asymmetry of the masses, there's a little secondary peak that starts appearing and becomes quite prominent when these two masses of the binary black hole are really asymmetric. Now, we use the same idea to basically discover the higher order modes from the GW190412 system. So this is the data from one of our detectors, the L1 detector or the LIGO Livingston detector, and you see that you can't make out anything. The entire signal is buried completely in noise. But when you take the spectrogram, you see a faint trace of the dominant mode. And this white trace that you see is where the next mode should have been, but we don't see it. Nevertheless, when you sum up the power or the energy along these tracks, you see that there is a huge peak corresponding to the dominant mode, and then there is this little bump when you sum up the energy along this white track, and this little bump is due to the energy from higher multipoles. If you listen to the um, equivalent sound of this wave without higher modes, this is what it sounds like. And if you now include the sound of the same signal, including higher modes, you know that when higher modes are included, higher multipoles are included, then it doesn't change the pitch, but it only changes the timbre or the quality of the sound. See if you can spot the difference in sound. So I'm going to play it one more time so that you can appreciate it better. But let's play this once. So this is without. And this is including. Right. So now that we have seen how we can extract or how we can detect higher multipoles from gravitational wave signals, I just want to spend the last part of this talk talking about how we can decode the information from higher multipoles. In other words, I want to talk about what they are useful for. So you have to understand that detection is just the first part of astronomy. So once you have detected, you need to understand or reconstruct the source that is emitting these gravitational waves. And once you know all its properties, what kind of properties are we talking about? We're talking about how massive is it? How fast is it spinning? Where in the sky is it? How far away from us is it? And so on and so forth. So once you can reconstruct the source, then you can start to do astrophysics with it. So once you have made the detection, you must decode the information that is coming along with the higher multipoles. And it turns out that information from the dominant and higher multipoles lead to a better source reconstruction. So how do we know what are the masses and spins of these binary black holes? So what you have is basically astrophysical signal in the detector which contains noise in it. Basically, we really don't know what nature has hidden in the detector noise. And then what you try to do is you subtract off the best possible signal that you think there is inside that data. And whatever remains, the residual of the subtraction, you try to understand whether the residuals are consistent with the noise in the detector. Of course, that has to be a statistical measurement. So you keep varying the source parameters of the signal that you think is there in the detector until all the residuals look like noise or as best as possible to the noise. And those parameters are the ones which correspond to the source. So that's how you reconstruct the source. So higher multipoles, when they are present in the detector, improve the accuracy of the source reconstruction. So here is an example of that. So for instance, here we have fixed the mass ratio. The asymmetry of the masses is always 10 to 1. So there is one black hole which is 10 times as massive as the other one. And what we are doing is we are increasing the total mass of the black hole. And on the vertical axis, you see these are the errors in percentage of a particular quantity that we can measure, which is known as the chirp mass. And you see that if you don't have higher order multipoles in the signal, then these errors can be very large as compared to a case where we have all the multipoles put into the signal. It also turns out that the more massive black holes, they actually emit at lower frequencies, and the higher multipoles, they come in at higher frequencies than the dominant mode. So for very massive black holes, you may be able to detect those very high mass black holes in the detector's bandwidth by including higher order multiple. So for instance, you see that beyond about a few hundred, 60 to 70 solar mass, the signal to noise ratio, if you don't include higher harmonics, falls very quickly. Whereas you can extend the mass reach of these detectors significantly by including higher order multiples. Here is a more modern version of this, the same picture. So basically, again, we split out all our systems in 2 dimensions. So one of them is the symmetric mass ratio. So this is quantity which tells you how symmetric the 2 objects are. So if you go from right to left, the asymmetry increases. And this vertical axis is the total mass. So you see that higher harmonics of gravitational wave signals are important for detection. For instance, highly massive and asymmetric systems can only be detected if you have higher multipoles in the signal. And the other area that is covered is basically an area where the parameter estimation improves significantly due to the presence of higher order multipoles. And this overlap zone that you see in darker gray area, that corresponds to the range of systems which definitely benefit from subdominant modes for both their detection as well as parameter estimation. So as I was telling you earlier, that higher harmonics improve our ability to reconstruct sources. So for instance, here is you pretend that there is an astrophysical source which has higher multipoles in it. And you're trying to estimate its parameters using just the dominant multipole, and you don't care about the higher order multipoles. It turns out that the systematic errors in total mass, this is that delta M, can be as high as 16%. Whereas if you do include higher order multipoles, this number comes down significantly. This is the same plot for a different system where there is no spin on the more massive object. And in this case, not using higher order multipoles actually results in an error of about 37% in the total mass. So basically, you will not be able to reconstruct the sources that are emitting these gravitational waves very accurately, and hence you will not be able to do precise astronomy with these sources. Although you might have detected it in some way, but still astronomy would be very far away if you do not include these higher harmonics. Finally, I'll come to the case where we show how, for the most recent event that was discovered in LIGO, this GW190412 event, how we were able to estimate the distance to the source and its inclination using higher order multipoles. So let me just explain what it is. So here are these 2 black holes that are going around each other. And this is the vector which is normal. This is the total angular momentum vector. And this is the line of sight. So from your detector to that object, so that is the luminosity distance. And this angle between your line of sight and the total angular momentum vector, that is denoted by theta jn. So this is just a symbol for that. And now what you see over here are the parameter estimation over the theta jn and dl. So let us look at the distance, and you look at this distribution. So this blue distribution is when you just have the dominant multipole, and with that you can see that it is kind of spread all over the place, and it would be very difficult to pinpoint how far away that source is. But as soon as you include this red dashed, which is the higher multipoles in the signal, you see that it kind of condenses to a more localized position in the cosmos. Similarly, for theta Jn, so with just the dominant multipole, the distribution over theta Jn is pretty wide. Whereas if you include higher multipoles, you see that you immediately converge to a much more localized theta Jn, and you can tell what is the inclination angle of that binary with your line of sight much more accurately. So finally, I would like to conclude by reminding that astrophysical merging binary black holes give off gravitational waves. And these gravitational waves contain a mixture of dominant part, which is at twice the orbital frequency, and also subdominant multipoles at thrice, 4 times, and so on of the orbital frequency. But these are usually much more fainter. And if you have more massive systems, so high total mass and more asymmetry in the masses, then it becomes important to include these subdominant components to the signal so that that you can search for them as well as for reconstructing the parameters of the source. The other thing that we looked at are ways in which we can separate out these components when they are present in gravitational wave data. So one of those ways is known as a spectrogram, which acts like a prism. So what they do is they unravel the frequency component of any signal. And the GW190412 was the first gravitational wave signal announced by the LIGO and Virgo collaborations, which seems to have higher order multipoles. And we are really excited about that. So with that, I end my talk. And I really thank you for your time and attention. And now, if you have any questions, you can redirect them. Yeah, so there is a very interesting question by Shravya Shenoy, and the question is, how do we know that the higher multipole signal is not noise? I think that's a fantastic question. So, in fact, that's why you need a statistical analysis. So you're absolutely right. So not only does the spectrogram separate out the components of the signal, but because the signal is embedded in noise, the same thing happens to the noise also. And noise has equal power. When you whiten it has equal power in all frequencies. So it's some part of that noise energy is also going to get into the track corresponding to the higher multipoles. And you might incorrectly infer that what you're seeing is an energy from higher multipoles. So what you do is we basically try to do a statistical analysis to make sure that the energy that you see is significantly more than what you would expect from noise alone. So that's how we know that that the higher multipoles are real and not because of noise. Swarangi Saraf has a question which says, what is the highest harmonic observed so far in the case of gravitational waves? So as I said, this is the first time the GW 190412 event is the first one where we were able to confirm the presence of uh, the octopole, which is beyond the dominant quadrupole harmonic of the signal. And so that's as far as we have been able to go. Bhasin Thakur has a question which says, does the recently detected asymmetric mass BPH merger have a similar spectrogram as shown in your presentation? That's absolutely right, Bhasin. So if you plot the spectrogram of the recently discovered event, uh, without noise, that is, if you add noise to it, then what happens is that at least visually you will not be able to see that other track that I mentioned. Maybe I don't know, something has happened to the presentation. I'm not able to go back. But the answer is yes. It looks very similar to the ones that I've shown you. Ayushi Chippa has a question. How do we know which harmonic is present while observing? And what is the significance of the prominent third harmonic? So we know, of course, when we do the search, we try to see which model of our signal gives us the most signal to noise ratio. So for instance, if we see that um, we improve our analysis by including higher harmonics, that's how we know which harmonic is present. And also by doing the spectrogram analysis followed by a statistical analysis, we can know exactly which harmonic is present in the signal. Atul Prajapati has a very interesting question. Does the match filter used in LIGO account for the multiple signals, or does it just use the fundamental signal for searching gravitational wave? That's a very good question, Atul. So as of now, we use only the dominant, the fundamental mode for searching for gravitational waves. We do not use higher modes. We use higher modes only in the post processing. So once we know that there is a signal, then we basically zoom in on that stretch of data which has that signal embedded or buried in it, and that's where we go all out and try to characterize the signal as best as we can. Basim Thakur has another question that's also very interesting. When we whiten the noise, how are we sure about not having whitened possible signals as well? So Basim, for that, there are standard signal processing techniques where, of course, when there is noise, when there is signal present in the stretch of data, you always run into an issue that is going to add power to that noise, and when you whiten it, you run the risk of whitening out the signal. So you use standard techniques in signal processing, which are known as Welch PSD estimates, where you use median estimates of the PSD or the noise power spectral density, which are not very sensitive to the presence of signal in the data. So Ayushi Rajgor has a question that says, how do we come to know if the gravity waves were emitted due to the merging of black holes or pulsars? So that we know by, so when we compare the signal shapes to the data, different masses actually lead to different signal morphology, and the ones which match best to the data often tell us whether these are black holes or neutron stars. And further, when we do parameter estimation, neutron stars can deform, especially during merger. And by looking at those kind of analysis, we can tell whether these are emitted by pulsars or black holes. Do we expect a loss of mass after merging of black holes due to gravitational waves? This is from Avinash Patro. Yes, we do. The final black hole is less massive than the sum of the components, which were merging components. There is a general question by Manisha Panigrahi. She asks, how can we start reading research papers produced on gravitational waves? Should we start by reading past research papers, and is rigorous training in physics required before we can start reading the current literature? So, as in all research, Manisha, the best way is to start doing a little bit of research yourself, and you throw a little bit of light backward whenever you need it, and you make steady progress, and that's how you pick up the thread, basically. So I suggest that you look for internship opportunities within LIGO India and elsewhere, and that's how you get an idea of what is going on in this research field. There is a question by Yuvraj Murali. The presence of multiple signals seem to be vital in the signal to infer more info, but is there a potential danger where the method implied to avoid noises eliminates these vital multipoles? Well, usually I think you are referring to glitchy data. And usually the tests which tell us whether a certain part of the data is glitchy has a completely different morphology and a different spectrum. So, so far we have been able to, avoid this potential danger. So I think does higher multipole get affected by the redshift of GW? So actually, the redshift shows up, in the masses and the luminosity distance, and basically it shows up in the way the fundamental frequency evolves. And these higher modes are just numerical multiples of the fundamental frequency. So however it affects the fundamental mode, it affects all the higher multiples exactly in the same way. There is one last question, which I'm not very sure I understand. Is by Viswajyoti Kaur. He asks, GW travel at the speed of light. Does the limitation to their travel velocity arise due to the space-time itself? I mean, is the velocity related to space-time? So in Einstein's gravity, the velocity of gravitational wave is exactly equal to the velocity of light. I hope I have been able to answer your question. But if there are other theories of gravity, or if there is if you have a theory where the graviton has mass, then of course that can change. So we can in fact put an upper bound on the mass of the graviton as well, using gravitational wave signals. So thanks a lot for your time. I think I'm not sure if there are more questions for me. Before leaving, I'd just like to tell you that the next talk is on unfolding mysteries of the universe with compact binaries, and that will be delivered by Professor Archana Pai from IIT Bombay. And that is on next Wednesday. That is the day after tomorrow. So I hope many of you will join Archana in this talk. Thanks a lot for your time and also your patience.